Hello everyone, hello students. Today we will be deriving the current equation for the N-channel MOSFET. So let's recap what we have done in yesterday's class. So yesterday's class we have started with the NMOS structure. Let me just draw it again for your reference. So we have a gate terminal, then followed by the oxide layer. Okay, this is my oxide layer, and then we have N plus diffusion. So this is my N plus diffusion region. This is P plus diffusion region, and then later on I have a P substrate. So here is my P substrate. Okay, yes or no? Then I can take this as a metal gate. This is gate. Oh, I have drawn something wrong. What is the matter? Here, from here to here. Correct? So I should have some gap for the source terminal. What is this terminal? Can you tell me? This is N plus, this is N plus. What is this terminal called as? Anyone?
Body terminal.
Yes. This is body terminal. Normally body terminal and source terminal are at the same potential. We ground them. This is my drain terminal. Okay. This is my metal. This is oxide. Okay. This is oxide layer. And this is my N channel. Now N channel I am marking in red in color. So this is my N channel formed. Let's say it's uniformly formed. Okay. N channel is what is the other name for N channel? Anyone? What is the other name for N channel? Inversion layer. Yes or no? This we have P silicon substrate. So this is my, and my length of the channel is here. So this is x equal to 0. This is x equal to L. So this distance is my channel length L. So L is my channel length, which is an important design parameter. Okay, so let us discuss what all things we have discussed yesterday so far. So yesterday so far we have discussed about the characteristics of the MOSFET, right? So we have applied a small voltage, you remember 0.1, then 0.3, then 0.5, yes or no? Then we have plotted the output characteristics. We said that from 0 to 0.1 is almost a straight line. Then there is a bending of the slope. Then again the slope reduces. And then after 0.5 what happens? The current saturates. It remains constant. Now why it remains constant? You can check the recording of yesterday's class. So these are the points which we have marked. Okay. Now depending upon this, how many regions of operation we have over here? Can you tell me? Let's say your VGS minus VTO is 0.5. Okay, where VGS can be 1 volt, this can be 0.5, or this can be 1.5, this can be 1 volt. So VGS minus VTO is 0.5. Now can you tell me the first region of operation? The first point is over here. Okay, so first region of operation is cutoff mode. So in the cutoff mode, does the ID flow, current flow? No. So ID off is 0. What are the conditions? Channel conditions for the cutoff region? Yeah, tell me, I am not writing.
VGS is lesser than VTO.
Yeah, VGS is less than VTO, that means the channel is not formed. Second is linear region. Linear, or we call it non-saturation. Some people call it ohmic also. Here ID flows, which is called as ID linear current. So drain current flows. And what are the conditions? VGS is greater than VTO And what was the second condition, and can you tell me?
VDS is lesser than VGS.
Yes, absolutely. VDS is lesser than VGS minus VTO. That is absolutely correct. Then the third region of operation is edge of saturation, or what was the other name for it? Velocity saturation. Okay, so here what happens? ID flows. So what are the conditions? Can you tell me? Second condition is what?
VDS equal to.
Yes, equal to VGS minus VTO. And the fourth region of operation was beyond saturation. So in beyond saturation what happens? ID sat flows, the ID current saturates. So it's almost independent of the supply voltage. So VGS is greater than VTO. What is the second condition?
VDS is greater than VGS.
Yes, VGS is greater than VGS minus VTO. So if you have understood these conditions along with the working, half of your job is done for today. So this is the first condition, is the second condition. Very, very important table, by the way. If you understand this thoroughly well, more than half of your job is over. Now today's lecture, we will be deriving the expression of ID linear. We will be deriving this, and also we will be deriving the expression for ID sat. Now when we derive ID linear, we will be applying gradual channel approximation, GCA. And when we will derive ID sat, we will be applying channel length modulation, CLM. So both the topics are inclusive in your syllabus. Okay, understood? So next task is, first of all, the task of understanding the N channel MOSFET is complete. So this was N channel or NMOS enhancement type device. I hope you know the the symbol of it, how it is. Okay, we show 3 terminals, or you can show 4 terminals also: gate, drain, source. Or 4 terminal symbol is also valid. Can you anyone tell me the reason why is the dotted line over here? What is the meaning of this dotted line? Dotted line means that the channel is not yet formed. Okay, that means it is enhancement type. So that's why we draw the dotted line over here. Okay, these are the NMOS type symbols. So next task for today, which we are doing over here, is task number 1 will be derive the expression for ID linear, the current equation for the MOSFET in linear region. And second task is to derive the expression for ID sat. Now ID linear will be using GCA and ID sat will be using CLM. GCA stands for gradual channel approximation. It's a derivation. So derivation will come, I mean, it's inclusive in the syllabus. It will come in the exam. And ID sat is, we will be deriving under the assumption of channel length modulation. Okay, so explanation wise the working is completed. Now we will go to the mechanical steps and derive the expression for GCA and CLM. So for that I will go to my older PDFs. So I'll open the older PDFs, 29.A, gradual channel approximation. So is it okay if I cover it from here? Because that derivation is quite lengthy, so it will take a lot of time for me to write over here. Is it okay, everyone, if I use this for your explanation?
Yes.
Okay. Now gradual channel approximation, it's valid for long channel MOSFET. So what do you mean by long channel MOSFET? You have your drain terminal, source terminal, source N plus, drain N plus. So whichever channel, whenever the channel in the MOSFET is greater than 1 micrometer, that means if this length is greater than 1 micrometer, we call it as a long channel MOSFET. Long channel MOSFET. We have a short channel MOSFET also. Okay, so short channel MOSFET, the source and the drain regions are very nearby and they affect each other. So right now we are assuming that drain and source terminal are far apart, so the effect on each other is not felt. So It's valid for long channel MOSFET. So GCA will allow to decouple 2D equations describing the transistor into two 1D equations which can be solved analytically. You remember in mathematics 2D equations are really difficult to solve, the derivative, the integration, right? So GCA will allow us to decouple, break down the 2D equations into two 1D equations, 1 degree equations. So GCA will effectively reduce the analysis of 2D MOS transistor to 1D current flow problem. Okay, so this allows us to derive or devise relatively simple current equations which you can solve using your calculator also. Okay, which will be very well inconsistent with our experimental result. So GCA will also help in establishing the MOSFET IV characteristics. Okay, so what will be the outcomes of GCA? Their derivation for ID linear, ID SAT, and output IV characteristics, and we are going into picture context of N channel enhancement MOSFET. Alright, so can we start finally? Okay, so listen very carefully. I am not drawing this again, this has already been drawn over here. This is a cross sectional view of N channel operating in the linear or triode region. It's called as linear, triode, or non-saturation, one and the same. Okay, so let me recap. This is my P silicon substrate. This is N plus diffusion region for the source, N plus drain. Okay, my gate. This is my oxide, the blue color is my oxide. This is my N channel. What is this green color, light green color? Depletion region. And I hope you understand why it is more over here. Okay, this is my source region, this is my drain region. So let's assume my VGS is greater than VTO. Let's say this is 1 volt, this is 0.5 volt. VDS is less than VGS minus VTO. So if this is 0.5, VDS is less than 0.5, let's say around 0.1 or 0.2 volt. Okay, so these are the conditions for the N channel to be operating in the linear region. Okay, so this is my N channel. So if this is X equal to, can you see this yellow color? X equal to 0, X equal to L. So this is my channel length actually. So if you consider this as the axis, the reference axis, this is X equal to 0. So here we'll get X equal to L. So any problem in understanding this structure, everyone? Yeah?
No, sir.
Okay. EY is the electric field responsible for VGS voltage. Okay, so it will bring the minority charge carrier electrons near the Si-SiO2 interface, which will form the inversion layer, which will eventually form the N channel. Now EX is the electric field coming from VDS. Okay, so this will bring the electrons will enter the source region, enter the source terminal, will travel via the N channel, reach the drain terminal, they will be drained out from the drain terminal, and that is what constitutes the current inside your N channel MOSFET. Okay, so the current flows in X direction over here, not the Y direction. Okay, so this is my cross sectional view of N channel operating in the linear region. Now let's understand the working slowly, one by one. So here we assume that the substrate bias, the body, is connected to 0. So here VSB is equal to 0. Okay, alright. Here we say that VGS and VDS controls the drain current. So obviously VGS and VDS, drain to source voltage and gate to source voltage, controls ID. Yes, it does. It will control ID. Both of them control ID. We assume that VGS is greater than VTO, that is threshold voltage, and ND. I mean, see this doping concentration inside this N plus. Do you see why we write here P silicon? Because your doping can be Na, right? So Na doping can be anywhere around 10⁻16. Here we write N plus. So N plus doping will be very high, pretty high than we are assuming over here. So this can be 10⁻18. Here doping can be, Nd can be around 10⁻18. So more number of carriers are there over here per centimeter cube. Similarly here also we'll have Nd. So doping concentration is higher in the source region and drain region. It's highly doped. Okay, and whereas we have moderate doping for p-type silicon. So here is what is written over here. Okay, now let us go into assumptions. I hope it is clear so far. Okay, so we assume that VGS, let me just rub this out so that you have more clarity. We assume that VGS should be greater than VTO to create the inversion layer between source and drain. So we already know how the phenomena of inversion layer formation is. Now x equal to 0 here is at the source end of the channel. X equal to 0 is the source end of the channel, x equal to L is the drain end of the channel. Okay, understanding? And we are assuming that VTO voltage is constant along the entire channel. That is, the threshold voltage for this device is constant along the channel. That is the assumption. Okay, and we also assume the EX electric field is more powerful than EY. Okay, EX electric field in the x direction, that is lateral electric field, is greater than the horizontal electric field, that is electric field in the y direction. That is the assumption. These are all the assumptions. There are around 9 assumptions what we have written over here. Okay, first is VGS greater than VTO, x equal to L is at the source end of the channel, x equal to 0 is source end of the channel, x equal to L is drain end of the channel. Then threshold voltage is constant along the entire channel region, Ex is greater than Ey. Okay, here we have written what is Ex and Ey. Then the entire channel region between the source and the drain is inverted. Okay, that means the channel is present at the source and the drain end both. That is what we are saying. And drain current expression, drain current ID is due to electrons in the channel region traveling from source to drain under the influence of Ex only. So what we are saying is these electrons which are entering from the source terminal to the channel and then reaching towards the drain terminal, okay, are under the influence of Ex electric field only, not under the influence of Ey, because Ey has already done his job of creation of inversion layer. Okay, now it's the job of the lateral electric field Ex to take these electrons from the source terminal to the drain terminal, hence constituting current. Okay, so these are the various assumptions for the derivation. Everyone, any doubt over here? Any doubt? Okay, now why this is called as gradual channel approximation? You see, the channel is gradual channel means that the voltage varies gradually along the channel. You know, yesterday we have given an example VGC. What was that? Gate to channel voltage, right? Here it was how much? 0.5. Here if VDS is around 0.1, here it was how much? VG, yeah, 0.4. So what we are saying is the voltage is varying differently along the channel, right? Here the voltage is 0.5, here it is 0.4. So that is what do you mean by gradual channel approximation. Okay, I hope it is clear. So gradual channel means the voltage is changing gradually along the channel. Now listen carefully. This is just a 1D view. If I draw the 2D view of it, this is just the 1D view. If I draw the 2D view of it, see, it will look like this, right? The entire channel region will look like this. Yes or no? Are you able to visualize this? Hello? This 2D picture of it. This is the 2D picture of the same thing. Okay? So if I extend it below, I know this is the front view which I am drawing. If I draw the 2D picture of it, the channel will look like this. Yes or no? Remember it's a tapered channel. Now let me draw only the channel area, the channel region. So channel doesn't look like a. Let me draw it and show it to you. The channel is slightly tapered. Here, see, it's not uniform. It's slightly tapered like this. Yes or no? It's slightly tapered. It's not uniform throughout because of the drain to source voltage. Okay. What I mean to say is this: if I draw it slightly bigger, it's slightly tapered like this. This is the front view of the channel. Okay, but if I extend it in 3D, you know, direction, then it will look like something like this. Are you understanding? This is my channel. Okay, this is my N channel. Now let me show it to you. How will it look like? Yeah, it will look like something like this. This is straight. This is my N plus source end of the channel. This is my N plus drain end of the channel. This is my channel width, and this is my channel length L. See, x equal to 0, x equal to L. So this is actually channel length L from here to here. This is my N channel. This is how it does it look like. So this is my N channel, which is the inversion layer. Everyone understood how we have drawn this?
Yes, sir.
This is the 2D picture, simplified geometry of the inversion layer. As you can notice very carefully, the current will flow in 2D direction. Okay, I mean from here it will enter, and here it will go to the channel, and then it will go out. I mean, if you were thinking it will just a front view, no, it has an area inside. The electrons will go inside from here. See, n source, n plus source of the channel, they'll enter inside, they go to the channel gets tapered, then they leave the drain terminal. So this is the real picture of the inversion layer. So you might have to draw this in your exam also. So this is W is my channel width, L is my channel length. Okay, now what do we do with this? What do we do with this picture? So the starting point is to find the current flow in the MOS transistor. We need to know the charge Qi in the inversion layer. Okay, so we need to know charge Qi, ki how much is the charge over here, Qi, how much it is. Okay, what is Qi called as? Anyone? Inversion layer charge. Yes or no? So Qi will be, this charge is the total mobile electron charge in the inversion layer. Agree? Okay. Now, can you tell me this Qi, is it a function of x? Is it a function of distance x? So this Qi charge is different here and different here. Is it yes or no? So Qi over here, is it different? Yes or no? Tell me yes or no. Yeah, it is different. So Qi at x equal to 0 and Qi at x equal to L is different. That means Qi is a function of x. It's a function of position. So x is my position along the channel. Since VDS also varies going from source to drain, so VDS will also voltage vary, right? VDS here is different, here it is different, right? So therefore my channel voltage is a function of position. So my channel gate, actually we write gate to channel voltage, but it's okay. My gate to channel, we can write gate to channel voltage, or simply we can drop it to channel voltage, or we can write Vc of x. It's a function of x. So we can say channel voltage Vc of x is a function of x. Okay. Now what are the boundary conditions? What are the boundary conditions? Tell me, Vc of x equal to 0 is how much? What is the channel voltage over here? 0, correct? And what is Vc of x equal to L? What is the channel voltage over here? VDS. Agree? Hello? These are the boundary conditions for the channel voltage, boundary conditions. So right now if we see, the channel voltage at x equal to 0 is 0, and the channel voltage at x equal to L is VDS. Okay. Agree so far? So far so good?
Yes.
Okay. Now the applied drain to source voltage produces a varying potential Vc of x along the channel going from 0 to VDS voltage. Let's say VDS voltage is 0.1. So here it is 0.1, here it is 0.1. So this potential tends to reverse bias the channel N type to substrate PN junction. So this will reverse bias this diode. So this is P substrate, and I'll draw this diode over here. That means this diode, which is P silicon substrate and N plus channel, N plus drain region, it will reverse bias this. That's why we have a bigger depletion layer over here. Yes or no? So we will go by this. Yeah, what we were saying, the potential tends to reverse bias the channel to the substrate junction. Okay, so we have this PN junction over here, the substrate junction and the drain junction, the drain region. Okay, so the inversion charge can be expressed as follows. So tell me, what is the inversion charge? Formula क्या था पहले inversion charge का? What was VGC formula? VGS minus VTO minus, if VDS is 0.1, तो कितना होता था? Minus VDS, right or no? If this is 0.5, this will be 0.1, with VGC will be, example yesterday we have discussed this we have discussed already. Yes or no? At the drain end, whereas at the source end it will be 0.5 only, because VDS is 0. Yes or no? So at the source end it would have been VGS minus VTO, which is 0.5 only. Let's consider this as 0.5 because VDS was 0. So that's why we have written over here as x equal to 0, channel voltage is 0. Remember, the channel voltage and VGC voltage which we have discussed yesterday are one and the same. Okay. So now tell me, how do you determine the charge? Charge को कैसे determine करते? What is the formula for charge? Q is C into V. Yes or no? Come on, students. So QI will be C कौन सा इसमें? What is the C over here? Oxide layer ना, C ox. Now into which V? Vc of x. Yes or no? And this Qi charge is negative, so minus sign will come. So Qi is minus C ox Vc of x. Okay, and what is Vc of x? VGS minus VTO minus VDS. Yes or no? So see this equation, which if you can identify this, see this, VGS minus VTO minus Vc of x. Yeah, that Vd of x की जगह we can write Vc of x. Agree? Why minus sign? Because it's an inversion charge. Charge on the electron is negative. So Qi of x is minus C ox into voltage. What is the voltage? VGS minus VTO. Now instead of calling it VDS and 0, we call it Vc of x. Are you following? Yes or no?
Yes, sir.
See here, this is at the source end. So at the source end VGS is 0. We are calling it Vc of x equal to 0. Here, over here, the channel voltage is VDS, so we call it Vc of x equal to L. So that's why we have written over here Qi of x will be minus C ox VGS minus VTO minus Vc of x. So this we call it equation number 1. I hope it is clear. Its unit is coulomb per centimeter square. Alright. So the negative sign, as I have told you, refers to the fact that the charge in the semiconductor is negative on the n channel MOSFET. Now, what do is we take an element in charge. We want to find an area, right? So what do? We integrate. So integration के लिए we take a small patch of this entire chunk of n channel. So that small patch distance is x dx. Okay. So we take a small element from there and then we revolve when we integrate from x equal to 0 to x equal to L. That will give us the entire the current equation. Okay, the area which we can find out. Integration finds the area under the curve, right? So we are taking a small incremental segment of length dx. Okay, this is my incremental step. Can you imagine this? Dx. So length is dx, just remember. So we are taking an element in charge. So there will be a small charge over here. So इसके ऊपर charge क्या होगा? What will be the charge over here? dqi dash. Okay, small elemental charge qi. If qi is 100, dqi will be around 1. Very small value. There will be a small charge present over here in this incremental strip. So incremental charge dqi will be qi into w into dx. Now why we consider w now? This is the width, right? This is the width w into dx. So what is the area over here of this? This is looking like a rectangle, right? Length into width. So what is my length of this? Dx. And what is my width? W. So what is dqi? Qi into, how much it is? dqi? Qi into w into dx. बराबर ना? Hello?
Yes.
So dqi dash will be qi into w into dx. So we consider this incremental distance dx for the elemental charge qi dash, which we have discussed already. Now qi we substitute from equation number 3, equation number 1 over here, minus C ox VGS minus VTO minus Vc of x w into dx. Now we differentiate, as I told you. Now we have considered this elemental strip. Now we'll integrate from x equal to 0 to x equal to L. Okay, to find the area. So right now we are differentiating equation number 3 and then we'll take the integral. So if I differentiate this dqi dash charge by with respect to dt, what I will get? minus Cox Vgs minus Vto minus Vc of x into W dx minus dt. So only variable name is dx minus dt. Now what is current given by dq by dt? Yes or no? So this dqi by dt is my current only. So in this case id drain current is dqi by dt, which is independent of the position. Yes or no? Are you understanding? Rate of change of flow of charge is my current. So if I integrate this dqi by I mean dqi dash with respect to time, and I revolve this strip around x equal to 0 to x equal to L, I'll get the current expression. Agree? Can I start from, can I continue from here?
Yes.
So we differentiate this. So what do we get? id equal to minus Cox Vg minus Vto, actually Vgs minus Vto minus Vc of x, same thing, W dx by dt. This is nothing but dqi dash by dt. So we have written the same thing only, equation number 5, we have rewritten it. So dx by dt is what? If we differentiate position, you will get a velocity, right? We have a velocity, yes or no? So this velocity is called as drift velocity of the carriers. Remember yesterday we have drawn a curve for the velocity versus electric field, yes, and this was the graph of it. We told that after reaching a particular value of electric field, the velocity remains constant. This is the drift velocity, this is the Emax, this is the maximum velocity which it can handle, 10 raised to 7, let's say. So here it is a linear curve now, here it is a linear curve. Let me expand it and show it to you. Here it is linear, so the proportionality constant over here is mu. Okay, so Vd is proportional to Ex, electric field, and the proportionality constant is mu n. What is the mu n called as? Mobility of electrons. Okay, so Vd is the drift velocity, which is the average velocity of the electrons in the channel. See, all the electrons won't travel with the same velocity, okay, because there are a lot of inside the n channel also we have depletion region charges and other charges and all. They might hit them and the velocity might reduce. So all average velocity of all the electrons is the drift velocity. Mu n is the mobility of electrons, and Ex is my electric field, lateral electric field. Now how is Ex defined as? Ex we can define it as, I told you so, E is voltage upon length. In this case we have written Ex is minus dV by dx. So minus dVc by dx, lateral electric field. So what is dx by dt? Is drift velocity, which is nothing but minus mu n dVc by dt. Are you following? Equation number 5 and 6, did you understand why dx by dt is minus mu n dVc by dx? Understood this?
Yes, sir.
Because this is electric field, and electric field is a differentiation of voltage with respect to the position. So dx by dt is minus mu n dVc upon dx. Now assuming all the mobile electrons in the inversion layer have a constant surface mobility. Now it is not true practically, but we are assuming still. Remember, GCA, gradual channel approximation, is an approximation. There are a lot of assumptions over here. So one more assumption is this: assuming all the mobile carriers have the constant surface electron mobility mu n. Now put this in equation number 6, we get id is equal to mu n Cox W. Okay, we have rewritten it, we have written it in the equation number 5, we are putting equation number 6 in equation number 5. So id will be, the minus sign will go from here, right? This minus sign and this minus sign will disappear. So id will be mu n Cox W Vgs minus Vto minus Vc of x into dVc by dx. Understood everyone? How we got this? Check equation number 5 and 6. Yes? Yes or no?
Yes, sir.
Okay. Now dx we take it on the left hand side, so we have id dx and mu n Cox W Vgs minus Vto minus Vc of x into dVc on the right hand side. Now we integrate this equation number 7 along the length of the channel, that is from x equal to 0 to x equal to L. That's what I was saying. You consider an incremental charge and integrate it around so that we find the area. Now Vc of x changes from 0 to Vds. We know that, right? Correct. So we take the integral for equation number 7. So integral of 0 to L, x going from 0 to L, id dx. Okay. Now this also Vc going from 0 to Vds. Okay. Vc going channel voltage is going from 0, from source position is 0, drain position is Vds. So the channel voltage is going from 0 to Vds. So these are all constant terms, mu n C ox W, Vgs minus Vt minus Vc dVc. Okay. So what is integral of dx x, right? So here x is L. So we have id into L. Correct, na? This is correct, right? Then here it's the channel voltage which is the variable. So mu n C ox W is the constant. Then we have integral of x. Okay, here we have this. So it will be the same expression minus x square by 2. So integral of x will be x square by 2. Yes or no? So Vgs minus Vto minus Vc minus Vc square by 2. Agree? And what is Vc? Instead of Vc we have to substitute. Vc will go from 0 to Vds. So whenever Vc goes to 0, no need to write it. We directly substitute Vc as Vds. So this is the expression which we have written over here. Id is mu n C ox W by L. See, this L will come down. Vgs minus Vto into Vds minus Vds square by 2. Or if we take this half out, I will get id linear as half mu n C ox W by L twice Vgs minus Vto Vds minus Vds the whole square. So this is my drain current equation for n channel MOSFET in the linear region, and this is valid under two conditions. Okay, region of validity of this expression is Vgs should be greater than or equal to Vto, and Vds should be less than Vgs minus Vto. Okay, so this will guarantee that the entire channel between source and drain is inverted. So yeah, this is the derivation which you have reached up till here. So if they ask you in the exam, you have to derive up till here, id linear. So understood this? This is what we use in your labs, in your classes, either this equation or this equation. So half mu n. What is mu n? Mobility of electrons. C ox is the gate oxide thickness. W is the channel width. L is the channel length. Then Vgs minus Vto. Vds voltage is also there. Okay, everyone? Understood this? Hello?
Yes, sir.
Okay. Now let's write this equation down over there, where we have written the live one. Yeah, here. Okay, so we are writing it on for the linear region or non-saturation or triode region. Yes or no? So let us write the expression for id linear over here. Let's write it together. So id linear will be given by half mu n C ox W by L into twice Vgs minus Vto into Vds minus Vds square. Okay, here it is. Understood? Yes or no? So this is my expression, and this is validity. इसका validity किधर है? Already checked. Vgs should be greater than Vto, Vgs should be less than Vgs minus Vto. So it's validity. This equation is valid under these conditions. Vgs is greater than or equal to Vto, and Vds is less than Vgs minus Vto. So this is my id linear expression for using using gradual channel approximation. So under GCA, this is my expression. Okay, so at the outset, what can we say? id linear is proportional to W and inversely proportional to L. So channel length normally we don't change. If we want to increase the current, we can increase the width of the transistor, or see, it's proportional to C ox, or it's inversely proportional to T ox. So if I make my gate oxide thickness even smaller, I can increase the current. Yes or no? If T ox is reducing from 180 nanometer, I am reducing to 45 nanometer. So current will increase or decrease? Hello? If I am going from 180 to 45 nanometer, will id increase or decrease?
Please, sir.
Yes, of course it will increase. So drain current is increasing as we making the device dimension small. So this is the learning part which we learn. normally we don't treat it as a variable of VGS and VDS because they are changing. Okay, so design parameter is these things. Mu n is a constant. Mu n is mobility of electron, that is constant for silicon. Normally we assume it. Okay, so this is the expression, drain current expression for n channel MOSFET. So this is valid for n channel enhancement device. Okay, so this you should know without fail. This entire thing you should know. So this is my GCA, gradual channel approximation. Understood the derivation, everyone? Now see here. Understood this, students?
Yes, sir.
Okay. Now we can write the same expression as follows. ID linear is, we have practiced it again, half mu n Cox W by L twice VGS minus VTO into VDS minus VDS square. So we can rewrite this expression as follows. This mu n Cox W by L, we can write it as half Kn. You remember this term? We have used it in your labs. Okay, so here we can say Kn is mu n Cox W by L. Actually here also we can split it together. This can be termed as Kn dash. So Kn can be Kn dash into W by L. Okay, so we can say here it is, see, Kn dash into W by L. Alright, so under GCA, alright, are you concentrating on these terms? Because these are design terms. In your lab you substitute in your dot model this Kp term, right, and W and L. These are the parameters which we can change, Kn, Kp, W and L. Yes or no? You write na dot model statement in your LT spice, so we change that over there. Okay, agree? Okay, now remember this, we can derive ID in saturation also. So ID in saturation is given by what? ID sat. So here under GCA, the drain current in the saturation region is determined under following conditions. VGS should be equal to VGS minus VTO, edge of saturation, right? Yes or no? So for saturation we are substituting VDS is VGS minus VTO in the above expression. In the above expression we continue, so it will be half mu n Cox W by L twice, wherever we have VDS substituted by VGS minus VTO. So what do we get over here? VGS minus VTO the whole square. Here you will get VGS minus VTO the whole square. Okay, so what do you get finally? ID sat half mu n Cox W by L. Can you tell me what you will get? Twice VGS minus VTO square minus VGS minus VTO. What you will get inside? Hello? Only?
VGS minus VTO.
Yes, you will get only VGS minus VTO the whole square. That's it. This is my drain current. Okay, so many a times in your lower semesters you might have seen this is the expression. So let me write ID sat is half mu n Cox W by L VGS minus VTO. Okay, or sometimes this is called as VDS saturation. It's also called as VGS minus VTO. So sometimes these people call this also. So this is the expression for ID sat and derived under GCA. Now what are the conditions for the GCA? What are the conditions of the GCA? Can you tell me for the saturation region? VGS greater than VTO, VDS equal to or greater also. Yes, greater than. So edge of saturation and beyond saturation. So yeah, this is the equation of the drain current for saturation region. As you can see, it is independent of any VDS term. VDS term है ही नहीं इसमें, correct? Yes or no? So ID sat is a function of VGS only here in terms of voltages. It does not depend upon this thing VDS. Whereas ID linear, if you see, yeah, ID linear है, right? ID linear is a function of, is it both VGS and VDS? Yes or no? मतलब both VGS and VDS will affect ID linear, but ID sat को only VGS will affect, not VDS. Agree? So that means saturation current is independent of, according to GCA, independent of VDS. So it should remain constant, right? Yes or no? Hello? You're coming on to the very important point. Yes or no? Okay. Now see this. So equation number 9, this equation number 9 which we have derived, ID sat, is similar to what we have learned in your lower semesters. Now what is this we call this? We can call this as a constant, right? So ID sat, we used to write na this way in your lower semesters, Kn by 2 VGS minus VTO. You remember this? So Kn is this, mu n Cx W by L, and then story continues ahead. So it's the same equation which we have used in your discrete electronics. Okay, and this was the derivation today which we have done. Now let's plot the, so we have derived the expression for ID linear and ID sat using GCA. Now we will plot the curves. So this is how the plot will look like. ID linear, ID and VDS, ID versus VDS. Now as we can see very carefully, this is the locus. This is the linear region, saturation region. Now in the linear region, ID is a function of, let me write over here. In the linear region, ID is a function of VGS and VDS both. But in the saturation region, ID is a function of only VDS. Agree? So that's why when it enters the saturation region, it does not depend upon VDS voltage. It is independent of VDS voltage. That's why it remains constant. Yes or no? So yeah, please draw this graph, output characteristics in your books. ID versus VDS. We have a locus of points. We know why this is enhancing. Yesterday we have discussed. As you can also see, this distance over here with which we are drawing, it's not the same, it's increasing. It's not uniform. Okay, so this is my output characteristics drawn under GCA, gradual channel approximation. We have clearly distinguished linear region and saturation region. We have both the equations with us, which we have written up till here. Okay, very important. Understood, students? So ID under saturation is independent of drain to source voltage. It only depends upon VGS. Oh, sorry, wrong. I have written over here. It's a function of VGS alone, not a function of VDS. Okay. So ID is independent of VDS under saturation, and it's a function of VGS and VDS under linear region of operation. Okay, everyone? Yes or no?
Yes, sir.
Okay. Now small observations from the graph. For a very small values of VDS, for very small, let's say 0.1 here, can I say this is almost like a linear curve? It's linear, no, almost. Yeah. So for a very small values of VDS, ID increases linearly with VDS. Okay. Then drain current reaches a peak at VGS minus VTO, or VGS1 minus VTO in this case. It reaches these peaks. So there are 3 peaks over here: VGS1 minus VTO, VGS1 minus VTO, VGS 2 minus VTO and VGS 3 minus VTO. Okay. So at this at VDS equal to VGS minus VTO, what is this condition called as? What is this condition called as? Edge of saturation.
Of saturation.
Edge of saturation or onset of saturation. One and the same thing. So equation T is valid between this region. So see this equation number, the linear equation is valid from 0 to VDS going from VDS should be lesser than VGS minus VTO. So it's defining this locus. Whenever it is equal to, we are edge of saturation. Whenever VDS is greater than VGS minus VTO, we are in beyond saturation region. Okay, so this is what explanation is. This is explaining. Yeah, this is one and the same. So yeah, have you noted down this curve? Output characteristics of MOSFET.
Yes, sir.
Okay, all right, great. Now we move on to the second part of it. Yeah, in summary, these are the equations derived under drain current equations for the NMOS device. So let's rewrite it over here. So what are the drain current equations for NMOS enhancement type device? So ID off, when it is in cutoff, it is 0. ID, what is the condition over here? VGS less than VTO. ID linear equation is what? Half mu n Cox W by L VGS minus VTO twice, na? VDS minus VDS square. And what are the conditions here? VGS greater than VTO and VDS should be less than VGS minus VTO. Agree? Then ID sat, what was the equation? Half mu n Cox W by L VGS minus VTO the whole square. VGS should be greater than VTO and last one will be VDS should be greater than VGS minus VTO. Alright?
Greater than and equal to, right? As you said, from the ID side.
Where? Here also actually. Okay? So more accurate form. Yeah, this is it. So this is for this your N channel MOSFET device. So please write them down. This is what we have learning since 2 or 3 lectures. So we have derived the expressions for the drain current and the linear and saturation condition. This is GCA under gradual channel approximation. And you have drawn the current equation output characteristics under GCA only. Okay? Completed writing those equations?
Just a minute.
So this is what we have derived ID linear and ID sat. Alright? This you should remember it, you should be able to derive it as we have done today. Okay, so whatever we have been discussing today since for the derivation, if they ask you in the exam, you have to do it on your own. Alright, and you should remember each and you should understand the significance of each and every term. Okay, yeah students, can I move on to the next slide, next topic? Okay, so just not we will also learn the learnings from this equation. We will be learning from this equation. What are the learnings from this equation? So let's say we have ID linear equation number 8, which we are writing over here again. Now under very special condition, if we consider VDS is very much less compared to twice of VGS minus VTO. So let's say this, let's take some numbers. Let's say VGS value is I think this is the last topic for today. We are already saturated on time. So VGS is, let's say, 1 volt. VTO is 0.5 volt. Okay, so VDS should be lesser than twice of VGS minus VTO. So what is twice of VGS minus VTO? Can you tell me? 2 into 0.5, that is 1 volt. VGS should be very much less compared to 1 volt. Yes or no? For low, very low value. So maybe it's around 0.01 or 0.05 volt. Very, very less voltages. Okay. So for a very less value of VDS, very small value of VDS, can we say this ID versus VDS is a straight line? Yes or no? And then after that the slope reduces. We have seen this before, right? So ID versus VDS curve for the lower value of VDS is a straight line. That's why for this reason they call it as a linear region, right? Okay. So under these conditions we can say that this term over here dominates this term. VDS square term is very, very small, right, compared to this term. Yes or no? Hello. So if this is 0. See, I'll give you some example. So if this is 0.5, if VDS is 0.05, so VDS square will be 0.05 square. This will be small. So this quantity will be very, very small compared to this. That's why we have ignored it. So that's why we got equation number A. Now equation number A is clearly showing the linear relationship between ID and VDS. See, ID and VDS are not squarely related now. Okay. So if I differentiate this ID with respect to VDS, okay, what do we get? Mu n Cox W by L VGS minus VTO straight away. The all are constants. So what is delta ID upon delta VDS? Actually 1 upon that will be on state resistance of the diode. Okay, so R on, we get R on state resistance of MOSFET is 1 upon mu n Cox W by L VGS minus VTO, meaning we can use a MOSFET as a electronically controlled resistor. Okay, we can use MOSFET as electronically controlled resistor for very small values of VDS, right? We can change the value of VGS and the resistance will change. Yes or no? So this is one application of from the curve. Okay, so at very low values of VDS, NMOS behaves like a linear resistor. So R on can be varied by changing VGS. That's why it's called as electronically tunable resistance. Okay, so here we can say the NMOS can act as a voltage dependent resistor. Yes or no? It's R on voltage depends upon VGS voltage, because rest all the terms are almost constant. Yes or no? So this is one application of NMOS where it will behave as a resistor. Agree? Everyone? Hello? One of the applications of a MOSFET is at very low value of VDS, your ID behaves linearly with VDS, and under that conditions R on is my on-state resistance, which can be electronically controlled by controlling the VGS voltage. That's why it's called as a voltage dependent resistance under this conditions. Now another application is a switch. Okay, you can turn on and off the MOSFET just by applying. If it is on, it will behave as a on state resistance and a closed switch. If it is off, it will behave as a off switch. So where VGS is less than VTO, VGS greater than VTO. So we can use this MOSFET as a switch. So MOSFET as a switch on condition, it will be in saturation. Okay, and off condition will be in the cutoff mode. Not saturation, we can call it as a linear region. In the linear region the MOSFET is on, and the saturation it is off. So a very powerful application of a MOSFET, it can serve as a switch. Okay, so we can just turn on your VGS voltage greater than VTO, the MOSFET will turn on, and if we make VGS less than VTO, the MOSFET will turn off. That's what we want from the switch, right? On and off control. So this also we can call it as a electronically controlled switch. We can use it. So therefore MOSFET behave as a switch which can be controlled electronically by controlling the value of VGS. See, VGS greater than VTO, VGS less than VTO. So next application is electronically controlled switch. I hope you are following. Okay, so next time we will recap preview of the next lecture will be, we'll analyze the values, analyze the MOSFET for large values of VDS. How does the ID gets affected? Does the shape of the N channel change? Will it affect the output IV characteristics? So basically we will be discussing channel and modulation. Okay, so what is channel and modulation? Will it affect my already derived ID linear and ID sat expression? Will I get a modified IV characteristic? So all these questions in the next class. Okay, so that's all for today.